Yeah, with the problem that you're working on, let me mention that. Like, so I put pins at all these joints, right? You never buy a bicycle that has pin joints, or I don't recommend it. But but think about like trusses that you see in buildings and bridges and whatever. Um, you never see pin joints at those either, right? You see, uh, what would you call that? A gusset plate? I think that's. So you see these trusses, that have. I guess this one would be some kind of triangle or something. Who knows? Anyways, at any rate, they're not pins. Okay, they're like this. So why do we learn to do trusses with pins at the members? Because if you're expecting your if you're expecting your joints to apply couples to hold this thing together, those are going to get ruined right away. Okay, like if you so say instead of building a truss like this that doesn't require so right now you could put pin joints here at these three joints, right? And it would be determinate and you could calculate the loads and it would stay static, right? Even though these could apply couples, you're not requiring them to. Like what if instead you're like, oh, those things can apply couples. I'm going to just build my bridge like this, you know? Statically, it's determinate, but these things would immediately be destroyed, you know? Asking these to provide couples uh, causes a lot of damage in a hurry, okay? And so that's the same principle with the bike frame. Even though those are weld joints and they can apply couples, um, you don't really want to ask those weld joints to provide couples. I mean, I guess in some of those funky like fully suspended mountain bikes and stuff, um, you do use joints to provide couples, and I don't know, I haven't thought about right because you have things like you have like overhanging things and things that wouldn't if you put pin joints there they wouldn't stay in place. Can you picture the kind of frames I'm talking about? Like you have seat posts that aren't connected to the or whatever this is called. The what's that called? The,
Well, there's usually still a strut in between the
There's some that
back
don't do
half.
it.
There are? Okay.
Well, but
and then
it won't be coming straight from the neck usually, but it'll.
hmm, yeah, I mean, there's
Yeah.
crazier things than what I did on the problem, and I haven't thought about, um, statically what's going on there. But I put pin joints in our problem because these frames are designed um, not to require as little couple to be produced by those weld joints as possible, because asking for weld joints at those couples would always cause frames to break at the weld joints. So, anyways, that's the idea. That's why we're treating them as pin joints, even though they're not. It's the same reason that we treat bridge trusses as having pin joints when they're not. Okay. Anyone have any questions about that? Um, yeah, I'm glad to bring that up because um, that's sort of an important thing in all our discussion of structures and trusses and stuff. Like these, the trusses that we talk about don't look like the trusses that are built. Our trusses have pin joints, and you would never see a bridge with pin joints at those things. They're too. I mean, for one thing, they're probably too expensive to put together. Too hard to put together. Um, So why is that? Why don't we do what's really there? It's because we want to make the fact that those are fixed joints irrelevant, you know, when we design the bridge. Any other questions about the problem besides that? Um, there was one mistake. A few people emailed me about that. I said something like, um, I essentially I gave two lengths for the member BC. One of those was meant to be BD, and so that's corrected now. And basically the lengths all uh, look like what you expect them to look like. So there's the equilateral triangle, then there's the longest member, and then the second longest member. So these are all 54 centimeters. Yeah, and the long one's 58, and this one's 56. Yeah, but you're right, but I think in mine it's this way. You're right. The way I have it drawn here.
Can we fix it? So
And they're
like makes
almost
sense.
equilateral triangles.
I don't know. It's like it looks in the problem, not on here. Okay.
Oh, okay.
Although that's not completely to scale either. So.
It is to scale.
Right, but that.
But the lens is a fisheye lens. Okay. So that's it. So I said it was due on Thursday. Of course, well, maybe not of course, but if you want to turn it in Tuesday, that's fine. But the sooner you get it done, the less chance it'll be that it'll start to, that a new assignment will be given and you'll still have that one out. That's really the only issue. Okay, so now we're done talking about structures. I think structures, the last thing on structures was chapter 8, I think, in the statics book, although we're not following the statics book too much. Now we're moving on to chapter 9, I think, which is friction. We're following it in the order of topics, but a lot of the topics have been vastly different, vastly better, in my opinion. That's just one man's opinion. Me. Being one man. Yeah, in a sense. Okay, so this discussion of friction we're going to do in 2 days. The first day we're going to talk about, we're not really going to talk about wedges, but I think how to treat wedges is going to be sort of implied in how I do this discussion of the first day. But the main thing we're going to talk about is square-threaded screws. So I'm not going to talk about wedges because, first of all, it's pretty simple to figure out. If you had to figure it out, it really comes pretty directly from the friction stuff that you know from Physics 1121. And second, I can't think of any applications really where it's used. I'm sure there probably are some, but I've never seen them, so I'm just going to leave it alone. And then on Thursday, we're going to talk about rolling resistance, and bearing friction. And so the discussion today, that's pretty much entirely that's hard to say, square-threaded screws, is based on, so here's today, wedges and square-threaded screws. And this topic is just comes directly from the discussion of friction that you've already seen in physics. So it's based on the Physics 1121 approach, where you have blocks sliding on inclines at some angle. Let's say the mass here is 100 kilograms. And we know some coefficient of kinetic friction, and we know some coefficient of static friction. Which is higher? Static, yep. And so I'm just going to sort of ease us back into this. I'm going to do a quick problem. Oh, you know what? Sorry. Before I do this, I want to give sort of a general discussion of how friction would appear in the stuff that we've discussed so far. Okay, because these are kind of new topics. I mean, you could imagine a square threaded screw appearing in some statics structure or something, or you could imagine some static structure rolling and having rolling resistance or whatever. But I think the most obvious, okay, so step back. Where could friction appear in a structure and how would it change the problem? Well, so imagine a structure like this. You have this end pinned to the floor, pin joint here. This end has friction. There's something so it won't fall down, and then you're applying some load to it there. We have so far broken contacts like this up into, and I haven't done a lot of problems that had contacts like this, but when we talked about joints, I did discuss it. So far we've only had two ways to treat this: totally frictionless and totally rough, meaning it can apply any amount of friction required so that this doesn't move. Okay? So how would this problem change now if you had, what if now this wasn't totally smooth and it wasn't totally rough? So we had some, say, coefficient of static friction. Okay? What would change about this problem from what we do now? Okay, right. So, but think about, so that's how it would be different than if it were totally smooth. That's right. Like if it were totally smooth, we just have a vertical reaction force. If it were totally rough, we'd have, a force of friction vector. I guess the friction wouldn't. So we'd have a force of friction going that way and a normal going that way. How would that be different than what we have now that there's some limit to the amount of friction that can be applied? Like what's different in the totally rough case versus the limited friction case? Actually, it's just, no, so no, there's no difference. You treat it the same exact way, and then at the end, you just check your maximum force of friction and see whether it was enough to keep it static. you know? So it's really just a case analysis, you know? So the only difference between a totally rough contact and a known coefficient friction force is the last step. You just check at the end to see if the force of friction required for equilibrium is possible. Okay, so you treat it exactly, through the whole problem, you treat it exactly the same way you would for just a rough contact. You'd assume that there's this full force vector at this contact made up of the normal force and the friction force. You'd come up with a force of friction required for this to be in static equilibrium, right? You'd assume it's in static equilibrium, calculate the required force, and then at the end you just compare the magnitude of that force of friction to mu sub s times the normal. Does that make sense? You know what I'm talking about? Should we do that? Or is that a waste of time? Wait, waste of time? Yeah. Okay. So you know what I mean? So like when you first think about it, you might think, okay, we've been making all these idealizations, you know, either all the friction in the world or no friction. Like surely there'd have to be something different about how you do these problems. If there's like a physically, you know, physically occurring amount of friction. But it turns out for static things that there isn't, okay? For static things, you treat it like there's all the friction in the world, and then you just check to see if that's, to see if the maximum allowable force of friction is higher, is enough to produce the friction you need for equilibrium. Okay, so like in, say in this problem, I didn't do this problem, but say that you find that friction force, I guess in this case it would be negative. Like if you look at this, right, this would be pushing down oh no, it wouldn't be negative here. What I have here, this could be supported with, this could be supported even without that friction. So let's think of a problem like this, okay? So you push down, this thing wants to slide out to the right. And the question is the friction force pushing back to the left hard enough to keep it from collapsing, right? So say you find the force of friction is negative 100 newtons, and say that you find the normal force is 150 newtons. Okay. Then you just calculate the maximum force of friction, which is the static coefficient times the normal, which is 0.5 times 150 newtons. So 75 newtons, right? That's the max allowable for these two surfaces, these two materials. So the absolute value of negative 100 is bigger than 75. So these surfaces can't support that the required friction to maintain equilibrium. So the structure doesn't stay in equilibrium, it collapses. Okay, and in statics, that's all there really is to friction of structures. Okay. So I think, to me, like the interesting thing about that is that there isn't anything, there aren't any subtleties to friction in statics, kind of, you know? Like you treat it exactly like an idealized case with all the friction in the world and then just compare to your maximum to see whether that could happen or not. And the nice thing for us as the people who calculate the statics is like, oh, it moves. Send it down to the dynamics people, you know, which is you guys next semester, unfortunately. Okay, so let's go back to this problem. Just sort of a refresher. And we'll do this as a kinetic and a static friction problem. So we have 100 kilograms. I'm not going to apply any other external loads. Let's just deal with this. So the kinetic, I think I said, was 0.2. Static is 0.4. What are the units of the coefficients of friction? Yeah, no units, that's right, because you multiply them by something in newtons to get something in newtons. All right, so draw a free body diagram. And I guess we better decide which we're doing first. So let's first do the kinetic friction case. Say it's sliding down the incline. Okay. So we have a force of 981 acting down. And we have a normal force. And which way is the friction force acting? It's acting up. It's going opposite the velocity. And, okay, so these are the vectors, the force vectors. What about the coordinate system? How do we want to represent these? You remember how you treated these? I assume you did it the same way we do it, where you put the y-axis coming out of the incline, x-axis parallel to the incline. Let's make this, let's give this some value, 20 degrees. Okay, so that means that this angle here is 20 degrees. So Newton's second law says force of friction, normal, plus negative 981 times sine of 20, negative 981 times the cosine of 20. Is equal to, so in this case, this thing's moving, it's going to be accelerating. So this is equal to the mass times acceleration. We don't have in this class stuff on the right side very often, but we know it's going to be accelerating along the x-axis. So we have the mass times an acceleration with an x component and no y component. So equation 2 here gives us that the normal force is, did you calculate that? What's the normal force here? 981 times cosine of 20. $921? Okay. 921.8. And so, and then the force of friction, the first equation gives us this minus, what's 981 times sine of 20? 335.5. Is equal to 100A. And that force of friction is the coefficient of kinetic friction times the normal force. So you can calculate the acceleration. And what do you get there? What? Okay. Okay, so there's if it's a kinetic problem. For a static friction problem, I guess we have to, what we really want to find out is, does it move? So the free body diagram is going to look the same. (981) normal force. There's one thing we need to consider, I guess, about the free body diagram compared to the kinetic case. And that's the direction of the force of friction. It's not automatically the same, right? I mean, if, like, imagine that I had specified that at this instant the block was sliding up the incline, right? Like you could do that even though gravity would be pulling it down. You could push it hard enough that at the instant, the snapshot you're looking at, the block is actually sliding up the incline, right? Then gravity and friction would be on the same team, and you'd get a bigger negative acceleration, slowing it down, stopping it, right? So in that case, you'd get a force of friction that was acting down the incline, right? What's the direction of the force of friction in the static case? We don't have any, like in the kinetic case, the force of friction direction is just determined by the velocity direction, right? So what determines the direction of the friction force in the static case?
It goes against the direction which wants to.
Yeah, right. And you can think of, like you could think of it this way. I don't think anyone really calculates it this way, but in a pinch, you could do this. Do the problem without friction, calculate the acceleration that occurs, and then the friction force is going to act opposite that acceleration that would occur, okay, which is sort of a long mathy way of saying what you said. It opposes the way it wants to go, you know. So in this case, the force of friction is up because if we did this problem without friction, this block would accelerate down the incline, right? Down the decline, I guess. So this opposes the acceleration that would occur without friction. Okay, so Newton's second law says, I guess we can use these same values. We have negative 335, negative 921.8, 335.5, right? That's the force of gravity. And then we have the normal force and the friction force. And before I write this, let's think about this. Like, these are just going to be zeros. So why are they just going to be zeros? We don't know whether it's moving or not. That's what we're trying to figure out, right?
Trying to figure out how much it would take not to move.
Yeah, exactly. And really, it's the same thing as what I was trying to get at with this example. We're going to assume that it's static, figure out what that required force of friction is, and then compare it to the maximum. And if it's smaller than the maximum, it stays at rest. And if it's bigger than the maximum, we know it moves, right? So this is equal to zeros. So equation 2 gives us that the normal force is 921.8. Equation 1 gives us that the required force of friction is 335.5. Now we have to figure out what the maximum force of friction is. That's the coefficient of static friction, 0.4, times the normal, 921.8. And what's that?
368.7.
368.7? Okay, so does it move or not? No. So the maximum, so it's like friction's stronger than it needs to be in this case, right? So that's greater than 335. So the block stays at rest. Okay, so that taps into stuff you've done before. So now that we've done one of these problems, reminded ourselves how to do these, I want to bring up two main points about this stuff that are, I guess, that are important to keep in mind, that are going to come up in our next discussion. So notice two things. The first one is that the contact surface area doesn't matter. And that's a little counterintuitive. Okay, but we did all this calculation without knowing the dimensions of the box, right? As far as we know that, it could be 100 yards long or it could be the size of a dime, and that doesn't come into the calculation of friction force at all. Anyone want to comment on that?
Isn't that part of the coefficient or no?
No, it's not part of the coefficient. I mean, the coefficient takes into account like how rough or smooth the surfaces are, but that's all. So yeah, think about that for a second. What if this box, what I drew as a box, actually met the contact at a like razor sharp point? It was balanced up there, or maybe 2 points. Like,
It doesn't depend on area, right? Because
that's right.
I mean, I remember physics or something.
Yeah, you're right. I mean, so I'm just sort of trying to like elaborate on that because it seems a little odd. So I'm saying here's my what do they call those? Here's a paradox. Okay, so say that, so we just did this problem and it didn't depend at all on the shape of the contact, the surface area of the contact. So what if it met at two razor blades like this? Intuition tells you it's going to be a lot harder to move that thing, right? But really all that's going on there is, like, if you zoom in, that razor blade is just digging into the surface a little bit, right? And so you have a change in the shape of the surface, right? Now you have a flat surface here that can push on a flat surface here. So you're really changing the problem if you do that, okay? So this is relevant for any, okay, so what do I want to say? As long as these surfaces still meet in a flat way, it doesn't have any dependence on the size of the contact. Okay, that seems maybe a little counterintuitive, but that's just how it is. Okay, that's going to be important when we talk about square threaded screws. And the second is static and kinetic friction directions are determined differently. Okay. So now, based on those two things and that discussion of sliding along an incline, we can go on to this problem of square threaded screws. And I think the hardest thing about understanding this material might just be how difficult it is to draw this stuff. Like, really, I mean, it's, you know, it's just, it's not that hard to think about, but it's hard to get a picture in your head that you can't get on paper. So square threaded screws. So let's say that we have a screw with threads that loop around this way. Let's see. Okay. This is called a right-handed thread. And a right-handed thread is just one that obeys righty-tighty, lefty-loosey. You know that? Not rightly-tighty. So this is most screws. So if you, from above, if you turn it clockwise, if you turn it to the right, it's going to enter the material, right? And, oh, what does square threaded mean, I should say? So a square threaded screw means that if you zoom in on these areas, you don't have, I guess you could say, the edges meet the boundary at 90-degree angles. Okay. So we're not talking about like wood screws. Okay. And these are the kind of screws that you use in jacks and holding up supports. In order to use this kind of screw, you need to, it's like when metal meets in two places, right? And you have a machined, what do you call the track for the thread to go in? Whatever, like you have two machined parts, you know. It's not, so yeah, not wood screws, not things that are making their own path. Threaded nut. Yeah, that's right. That's right. Yes, exactly. Yeah, tapped, right. And the problems that we're going to deal with are, so you have this screw that you're applying some kind of torque to. And that's being used to support a weight W. And that weight W is supported by, now I'm going to take advantage of the fact that the surface area doesn't matter in these friction calculations, okay? Because you know there's a long surface area of thread that's touching this tapped portion of the whatever it's traveling in, right? But let's just assume, since that surface area doesn't matter, that what's really touching is just a single block like this, okay? Just that one single little place is traveling up this path. And it's being supported on a path like this. So in the next drawing, the part of the screw that's supporting the weight will have these horizontal lines, and the path that it's traveling will have the vertical lines. And just so, you know, to try to give a sense of how this thing is shaped, the path that this little tiny block of screw thread is touching goes around like this, okay? So if you apply this torque, right, from below, that's a counterclockwise torque. No. From below, that would be a clockwise torque, right? This block is going to slide up that incline. Okay, can you follow what I'm saying? Okay, so let's look at it from a side view. So this guy, looking from there, sees an incline facing this way. And that's the vertical stripe part. This angle is theta. Sees this block sliding on the incline. That's the horizontally striped part. And what loads are acting on this block? The weight, and that's going to be acting just straight vertically down. And then there's going to be some force that's produced by this torque, right? The torque is being applied to the screw. So you can sort of picture, if you think about this block sliding up this incline, that torque is pushing the block up the incline. We'll get into how to calculate that later, but I'll just call that a horizontal force Q. Okay. Okay, so these are the forces that are sort of fighting each other. There's the horizontal force being applied to slide it up the ramp, and there's this weight force sliding down, and friction is going to come into it. But first, let's figure out what would happen without friction. Okay, and why is that important? Because that's going to determine the direction that the friction force acts. Okay, and we're going to have both cases. Okay. Okay, so do a free body diagram of the block. There's the weight. There's that horizontal force Q. We're assuming that the weight of this tiny little block is pretty negligible, so I'm going to just leave that out. Obviously, I think it makes sense for any engineering application that weight W is going to dwarf the weight of the screw. So I'm just going to ignore that. And then, okay, so what other force? One more force.
Normal.
Yeah, normal. And we're leaving friction out for this part, so there's just going to be that N. And I'm going to do what I just did in the example, put the coordinate system tilted parallel to the incline. So Newton's second law says negative W sine theta, negative W cosine theta, plus Q cosine theta, negative Q sine theta, plus 0n is equal to the mass, I'll leave that as m, times A0. And the second one calculates the normal force. We don't have any use for that right now. What we want to know is the direction of that acceleration, okay, because that's going to tell us the direction that the friction force acts, under what conditions. So we get negative W sine theta plus Q cosine theta is equal to MA. So what direction does the friction force act? Like what direction is the accel? The friction force is going to be opposite that. By the way, let me just point out with this stuff. Like I know in a lot of classes, and probably in this class sometimes, I'll go. You know, people go through derivations that just sort of get you to the stuff that, to the equations that you're going to need to use. But you need to follow this because this is the kind of stuff that you're going to need to do in these problems. Okay. We're not going to just end up with like a set of equations to use. It's just going to take this sort of friction analysis each time. Okay, so I mean, what if Q is 10,000 and W is 10? The acceleration is down the, down the track. What if the weight is 10 and W is 10,000? Then it's going to go up the track. Okay, so what this says is the acceleration can go either direction depending on the values of W and Q. Okay. And so that means the force of friction can be either direction depending on W and Q. And what we are going to want to do when we include friction now is we're going to want to find critical values of W that define the boundaries between static equilibrium and motion. Okay, we're gonna figure out at what values of W is this screw just about to start unwinding, and at what values of W is this screw about to start tightening. Okay, that's what we're looking for. Okay, so let's first figure out, so now include friction. And the question is, at what value of Q is the block, which, remember, represents that whole thread of the screw, about to start sliding up the ramp. In order to do this, we're going to use the same approach that we used with both of these two static friction examples that I already did. We're going to assume static equilibrium. We're going to choose the direction of the force of friction based on what acceleration would be if there was no friction. okay? And then we're going to compare the required force of friction to maintain static equilibrium to some maximum value, okay? So the sort of the geometrical thinking of these problems gets tricky, you know, but all the physics, it's fundamentally the same as just blocks sliding up and down inclines, okay? Okay, so draw a free body diagram for this case. So we have Q. W. Normal. And in this case, which way is the force of friction going to act? Yeah, that's right. It's going to act down the ramp. Without that force of friction, it would have already started accelerating up the ramp. Okay, so the friction has to oppose that motion that's about to start happening. And this force of friction we're going to assume is equal to the coefficient of static friction times the normal. Okay, so we're going to assume that we're right at that boundary between rest and motion. Okay, and where the value of that force is at that point as big as it can be, right? These two surfaces can't produce any more force than what we have at this instant. All right, so Newton's second law says negative W sine theta, negative W cosine theta, plus Q cosine theta, negative Q sine theta, plus 0n, plus negative mu s normal 0 is equal to zeros. The second equation gives that the normal force is equal to W cosine theta plus Q sine theta. And now we can plug that into the first equation, and we get negative W sine theta plus Q cosine theta minus mu sub s times all this stuff, W cosine theta plus Q sine theta is equal to 0. And so simplify that, and you get Q times cosine theta minus mu s sine theta is equal to W times sine theta plus mu s cosine theta. And I suppose, actually, I asked for a critical value of W, so let's just isolate W. So W is equal to Q cosine minus mu s sine over sine plus mu s cosine. Okay, now let's do the same thing and figure out the critical value of W before it starts to slide down the ramp. So the free body diagram looks almost the same. What's different in this case? Yeah, the friction force is just going the opposite direction. So we got W, Q, normal. And then this time, without friction, it would be sliding down. So the friction force is acting up. Same coordinate system. Newton's second law says negative W sine, negative W cosine, plus Q cosine, negative Q sine, plus mu sub s times the normal, that's this, and then I'll lump those two together, is equal to zeros. Equation 2 says the normal is equal to W cosine theta plus Q sine theta. Put that into equation 1, and you get negative W sine plus Q cosine plus mu s times the quantity W cosine plus Q sine is equal to 0. So you get W times negative sine plus mu s cosine plus Q times cosine plus mu s sine so Q times cosine plus mu s sine is equal to W times sine minus mu s cosine. So W is equal to Q times cosine plus mu s sine divided by sine minus mu s cosine. So which of these values, like what do you expect as trends for these values? Like this critical W compared to this critical W. I mean, just think physically about that block sliding up and down the incline. I mean, you expect no matter what the force of friction is, no matter what the angle is, you expect this case where we have impending motion going up the ramp to be at least more positive than this, right? And probably for whatever friction we expect this one to be positive and this one to be negative, right? I guess from our experience with turning screws and stuff, right? But you could imagine a slope and a slope of the ramp and a friction force low enough that that wouldn't necessarily be the case, right?
I think it would work better if you solved for Q.
Really?
Well, because then you could see the torque, because the weight's really not going to change, right?
That's kind of the way that there's kind of like failure 24.
Oh,
Well, it's sort of like, yeah, like how much force do you have to apply? So if you're turning this screw, you know, like you have a car resting on this thing and you're turning this screw, like how much force? I mean, it's in terms of a oh yeah, wait. Oh yeah, totally. You're right. Yeah, I meant to solve for a Q. Yeah. Yeah, sorry about that. Yeah, let's do that.
I mean, basically, it's gonna
Yeah, you're totally right. Yeah. That's not what I meant to do. I got those two confused. So just erase that in your little electric board. Okay, so yeah, we want Q. So W times sine theta plus mu s cosine theta cosine theta minus mu s sine theta. Okay, and over here, Q is equal to W sine theta minus mu s cosine theta divided by cosine theta plus mu s sine theta. Okay, so that Q has something to do with the torque, right? And we haven't really thought carefully yet about what it does, but that force Q is what's pushing the block up the incline, right? And so if you're trying to get the block to start moving up the incline, you're going to have to apply a bigger force upward than you are if it's going down. And probably to go down, you're going to have to apply a force downward, right? And you see that here, that for the force upward, you have something bigger on top and smaller on the bottom. Over here, you have something smaller on top and bigger on the bottom. Okay, so that trend shows there. So now let's talk about how you get these values that you need here. What does this Q mean? How do you get this theta? Okay. Um, so say this is your screw. Then the distance from the edge of the thread to the center of the screw, I'll call the radius r. Okay. Um, you're usually going to have to get that angle theta from the lead or the pitch. They're slightly different in meaning, but in a lot of cases, you can treat them as interchangeable. But the lead is just the distance from, one point to the adjacent point on the next thread, the next time the thread comes around. Okay.
Lead to sameness, like frequency then.
Yeah, I mean, frequency is time. Yeah. So now how would you get that angle from that? Think of unrolling unrolling one whole revolution of the thread. Then this height is the lead. Okay. This distance is 2 pi r, just one circumference. This is the angle that we want. So the tangent of theta is equal to the lead over 2 pi r. So you can get that angle as the inverse tan of L over 2 pi r. Okay, and how about Q? What's the meaning of Q? Well, if you think of Q as just a force being applied at a distance of r from the center of that screw, then the torque T that I described back here somewhere, okay, the torque T that you're applying to this is just equal to Q times R, right? So Q is just equal to T over R. Okay, so next time let's do this example problem. Say that we have a left-hand threaded screw. Let's say that it has a lead of 5 millimeters. A radius of 10 millimeters. A coefficient of static friction of 0.7. That's That's about what you expect for steel on steel. It's supporting a load of 10,000 newtons. And the question is, oops, how much force do you have to apply to a crank arm of length 25 centimeters to lift that weight? Okay. Anyone have any questions about that? Okay. Do Thursday? This problem? Yeah, do this one too, please.